Yeah, honestly, yeah. Let's jump into it. So yeah, this is the first sort of intro to disruptive tech. I'm gonna go over. I'll go to the agenda. I'm gonna go over a little bit about who we are, what the deal is with this new division, and then I'm gonna dive into some technical details on quantum computing and blockchain. Um, so that's super exciting. Let's get into it. But before, I just wanted to say a huge congratulations to all of you. This year, Disruptive Tech was like the second most in demand division in all of QMind. We had something like 32 people put it as their first choice, another 36 as their second choice. And so there's a lot of like really great talent interested in joining this team. And unfortunately, we had to turn away some really solid candidates just because of capacity, which is something that I really don't like to do, but had to be done. And the fact that the 16 of you guys all made it through is absolutely amazing. You should really take a second to be proud of yourselves because you're incredible, and I'm super excited to have each and every one of you on the team. But who are we? Well, this is your executive team for the year. This is me. I'm the director of Disruptive Tech. I'm in fifth year Eng Phys Comp, coming off of internship. And yeah, you can feel free to reach out and say hi if you ever want to. We've got Spencer Hill over here. He's in third year Apple Math in comp. And then Paul is in fourth year Eng Phys Comp. Bhavon is in fifth year mechanical, coming off internship as well. And then Mustafa is in second year computing. So we've got a whole bunch of awesome talent, and these guys are all super nice. They're super friendly, they're really smart, and they've planned some really sick projects for you guys. So feel free to reach out if you guys have any questions, QMind related or not. They'll be able to help you out. So why are we here? What's the deal with this new division? Well, yeah, I touched on it a little bit in the introductory presentation, and really we're here to embody like a similar vision of what QMind was founded on, right? The idea of democratizing interesting and powerful technologies that you don't get exposure to until graduate school or maybe in your internships. But yeah, we're just extending the scope beyond AI. There's not much more to it, but why? Well, a couple reasons. One, we're going to try to position QMind really as like the tech club in Kingston, or in QMind, or in Queens. It's got a place for everyone, regardless of what they're interested in, what their technical skills are. We want to empower smart, like driven students, like all of you, to explore new technologies that you're interested in or that you're passionate about, and then give you a way to share that passion with others. And we want to build like a structured sort of development process so that when we have new ideas for new initiatives and new divisions within QMind, this disruptive tech division gives us like a sort of platform to develop those ideas, gain some traction before we make a whole new division or whole new club. And doing so, it kind of acts as like an innovation pipeline for QMind to constantly be trying new things and constantly improving. And really, the fundamental goal is learning. That's true I think it's true for all of QMind, but especially this division. We want to learn. We want to learn some cool stuff. We want to learn about new technologies, new fields, new opportunities, and so that's what we're here to do. So Sydney sort of touched on this in the introduction or opening ceremonies, but yeah, basically what your year looks like. So this weekend is going to be awesome. It's going to be sick. We're going to start off with some awesome technical workshops put on by myself and the other project managers. There'll be a couple like lectures or other events. There'll be a social tonight, which I don't know what that's going to be, so I'm super pumped to see what that's like. And there'll be a hackathon tomorrow. And that's where you really just get to test out your technical skills that we've been learning today. and the winner gets a prize. So we'll talk more about that tomorrow. And then looking over into the next month, that's where we actually split into our teams, and you start working on your projects. But so since this division is a whole bunch of new technologies and a whole bunch of new stuff, I really wanted to start with a heavy emphasis on onboarding. So you'll have some project specific work to like get everyone onto the same page, because some people might be like me in fourth year physics or in phys, and they know a whole bunch of quantum mechanics, and others might not. So we have to sort of balance that ground of get everyone on the same page technically as far as math, physics, coding, and all the relevant skills. And then we actually get to dive into the project and do some really cool work. So there'll be 4 different projects that we're running. You'll be part of one of them with a team of I think like about three others, and then the project manager. What those are, or what you'll be put on, we're gonna figure that out later. I'll send out something to sort of gauge what you're interested in, and then we'll split up. And then finally in March, that's QCAI, that's the undergraduate conference on AI. So what that looks like for our new division, we're not too sure yet. That'll be something we'll figure out as we start planning QCAI more. But yeah, stay tuned for that. So awesome. Let's get into the technical details and start learning something cool. So quantum computing, what is it? Well, really, it's best to just compare it to what we all know, which is classical computing. I think this figure does a really good job of sort of visualizing the fundamental difference between quantum bits and classical bits. So classical bits here, they have a value of 0, 1, on, off, up or down. It's a binary system, and the value of which is called the state. So it could be in the 0 state or the 1 state. And not only are these states, discrete, they're also deterministic. You can predict with absolute certainty what the state will be. And you can also apply sort of gates or operations like and, or, not, copy to sort of manipulate these bits and manipulate the information. And these gates can be a whole bunch of different things. They can have like a 1-to-1 mapping, so 1 bit in, 1 bit out, or they could take 2 bits in and turn 1 bit out, or take 1 bit in, output 2. And so that's like, that doesn't sound that cool, but it's a big difference between one thing that quantum bits can do, which we'll touch on later, is that all their operations have to be reversible. So it has to be 2 bits in, 2 bits out, and you have to be able to reverse that operation, and you can't like copy or destroy information very easily. But yeah, so what's a qubit, or what's a quantum bit? Well, the state's a little bit different, and that's why it's so interesting. So it can be a 0, 1, or it can be a combination of the two. And that's what's referred to as superposition, which I'm sure you may have heard of. And superposition it's literally just a linear combination of the 2 states. So we'll explore this more in more detail later, but there's a really, really deep and fundamental tie between quantum mechanics and linear algebra and probability. And so this is just sort of like the first example of this linear combination of two what are actually vectors. And what's nice about this graphic up here is actually that you can represent the state as like a point on a sphere, on the surface of a sphere, which is something that we kind of touch on in more detail later, and we can actually have some really nice visualizations of what the state of our qubit is by looking at the sphere. But let's I guess dive in a little bit more about what the difference between qubits and classical bits are. So an analogy that I really like is a coin. It's a pretty classic analogy, but I think it does a great job. So in the classical world, you can have heads or tails, right? You can have that's the state. It's the if it's a head or if it's a tail. In the quantum realm, it can be a heads or it can be tails, but it can also be spinning. It's my little graphic. And so that spinning kind of resembles what a superposition is. You know, it has a probability of being heads or tails, and it also demonstrates a quantum phenomenon called measurement. And what's weird about quantum measurement is that it's an irreversible change. That's one of the few operations that's actually irreversible that you can perform. So measuring a coin, right? So let's say you have a spinning coin on the table. To measure it, you could like slap it on the table to flatten it into either heads or tails. And you really collapse this spinning state into one of these two outcomes. And after this point, once it's measured, once it's in heads or tails, you can't reverse. You can't go back to that spinning state, and you lose all that information that was encoded in this superposition state of spinning. So what actually is a qubit? We know the differences, but what if you saw a qubit on the street? What would it look like? Well, that's a big question, and it's something that we will sort of touch on here, but it's it's a big question. So formally, when we talk about qubits, we are talking about an abstract mathematical object. Specifically, a qubit is represented formally by a two-dimensional complex vector space with an inner product. So what does that mean? Like really kind of just a bunch of math jargon that we don't worry too much about. They're vectors, as we can see here, and they're complex vectors that have some sort of amplitudes or coefficients that make it a linear combination. And the reason why we use this abstraction was it's not impaired yet, but it lets us deal with all the cool information processing tasks that we can and manipulate them without really getting tied down in the physical implementations of qubits. Because, frankly, we don't care too much about the physics behind it yet, or like how these qubits are actually implemented. Right now, for our purposes and for really all of our projects, we're dealing with the algorithmic side. So we don't have to deal with all the hairy physics that arise when you actually analyze this. And it's also nice because there's a lot of different physical implementations of qubits. So you could have like superconducting qubits, which are super popular, photonic qubits. Those are the two big ones that are seeing a lot of attention recently, but there's also like ion traps and topological qubits. And so we can just deal with these vectors, and that's good enough. And another analogy, if you don't love the spinning coin, is an electron sort of spinning on an axis, right? It could be spinning up or down, or it could be spinning in any sort of different orientation. And that's a little bit more representative of what the actual physical system is. So let's get into the notation here. I'll be periodically checking the chat, but put anything in there if you have any questions as I'm going on. But notation. So yeah, as I said, qubits are vectors, and we represent their state as such. So you can see here, this is the zero state in these funny little brackets. It's Dirac notation, but they're just vectors. And you can see this is what a 0 looks like. This is what a 1 looks like. And if you remember from lineage, these two vectors form a basis or a state. So any qubit state, any generic qubit state that you want can be formed as a combination of these two. So that's awesome. That's where superposition comes from. And what do we got over here? Well, this is really our generic cubic state. That's what I'm using to note the generic state. It's a Greek letter called psi. And if you're familiar with the Ninja Turtles, you might think that it looks exactly like Raphael's weapon, and which it does, because those are actually called psis, but they're spelled differently. So that's a fun bit of trivia. And these sort of coefficients here, alpha and beta, those are amplitudes. They're complex numbers. They denote sort of like how much 0 and how much 1 is the state. And they're not exactly the probability of measuring either 0 or 1. But they're very related to like, if you were to essentially square each of those, then you get the probability of measuring each state. So that's great. And just like in lineage, if you have these vectors, you can do an operation. And these operations are represented by matrices, they're transformations. Sometimes they change bases, sometimes they don't. But anyways, we can see here, this is a classic example of the NOT gate or the X gate. And it essentially just flips the 0 to the 1, the 1 to the 0. And you can see it has its representation in Dirac notation, but also in the matrix notation. We can get, studying quantum computing or quantum mechanics can get really mathy really quick. And I'm really just scratching the surface here because I don't want to try to overwhelm you too much. I'm sure I am a little bit, but we're also releasing a primer that I wrote that will sort of dive into the more nitty-gritty details and get you up to speed. But let's take a look at some other operations. So here are 4 that I just thought were really important and that you'll see a ton of. So I should touch on first that quantum algorithms are represented as quantum circuits. So like a circuit, you have these little wires here. And so they start from the left and the wire comes in, and the wire is just a qubit. And then you apply this gate, which is an X gate here, and then it outputs some sort of state. So that's the same for all of these, and they all have their certain symbols. Thanks, Mustafa. And so the first one, poly X gate, is what we sort of touched on already. There's like a poly set, which it doesn't really matter. They're just, they correspond to really 3 axes of rotation. So I touched on how a qubit can be represented as a point on the surface of a sphere, right? So you could have 3 axes to rotate that qubit and rotate the state of it. So there's poly X, poly Z, and then there's another one called Y, which I didn't include here. But the effects are quite simple. The X just flips it from 0 to 1, 1 to 0. You can see the effect on the generic state here. It essentially just flips the amplitudes. The Z gate that's an interesting one because it's also called the phase gate. So essentially it just applies a phase to the 1 state. What that means, what that implies is it a little bit out of the scope of the presentation, but you can do a ton of cool stuff by taking advantage of this relative phase. If you were to just measure this, you get the exact same result or distribution as you would as this, because this phase isn't really measurable, but there are cases where you can sort of interfere different states to make things more likely to be measured, or you could also change the basis that you're measuring in, and then that will result in measurable effects. So moral of the story is phases are really critical to quantum algorithms, and they can do some really cool stuff. Then there's the Hadamard gate. This is another big one, H, is what it's represented by, and it's really like the superposition operator. So it takes a 0 state and puts it into an equal superposition of 0 and 1. Right, each of them have an amplitude of 1 over root 2. Why root 2? Well, it's just a normalization thing. States have to be normalized just so that really the probability would then sum to 1. It just makes physical sense. Don't worry too much about that, but here you can see that each of them have a probability of a half. And then the Hadamard gate on the 1, it just introduces a negative phase here. Same kind of thing. The controlled NOT gate, that's our first multi-qubit gate. This one is it's exactly what it sounds like, a control knot. But if the control qubit is in state 1, then it'll apply an X gate to the second qubit, to the target qubit. Why? Well, it's a lot of reasons. You can see the effect here. If the target qubit, the control qubit, which I'm denoting as like the very first qubit, if that's in 0, it doesn't do anything. If it's in 1, then it actually flips it. And this is a really cool demonstration of it down here because we're already in a superposition of two qubits. But it's a pretty special superposition because then if you apply this C naught gate, then you end up with 0, 0, and 1, 1. And this is actually called a Bell state. It's super famous. And I talk a little bit about why in the primer, but you can see that if you measure one, it like instantaneously changes the other. Yeah, that's what that means. Really, these are just some operators, and I cover them pretty quick, but there's some that you'll probably see in the next workshops, especially this Hadamard ZNX gate. And we'll dive more into them in more detail to them in the primer, and feel free to ask any questions if you ever need to. But now I like to talk about why quantum. Because it's weird, you know. And it's expensive. Like building a quantum computer is not only tricky, but a lot of specialized parts go into it. So let's understand the motivation and the benefit that quantum computing could provide. So even with supercomputers, some problems are simply intractable. Supercomputers aren't that super sometimes. And what that means is really they can't do everything. There's some points that are just infeasible for them, or some problems that are infeasible for them to solve. And so a good example of this is the factoring problem, factoring large numbers. And that's really the basis of a lot of cryptographic methods that are protecting our banking statements and whatever. And I'm sure you may have heard of Shor's algorithm, which is like sort of the staple quantum computing algorithm that really is popular because it demonstrates the power of quantum computing in a very real sense. And it's one thing that motivated a lot of research. So I'll talk a little bit about that, but really the advantages of quantum computers, they go beyond factoring, that's for sure, but also like not that far beyond. It's important to dissect the reality from the hype behind quantum computers. And I'll touch on that at the end of this slide, but they are really cool. So let's talk about why. Shor's algorithm is an example where you're able to achieve an exponential speed up on a certain problem. And in computer science terms, that's a huge benefit. You make something that takes an exponential number of operations to solve and reduce it down into what's called polynomial time, which is way faster, especially as the size of your input, the size of your problem gets bigger. So there's also cases in which it can become intractable to simulate quantum algorithms purely based on memory. So in Shor's, we're talking about leveraging quantum effects to reduce the number of operations, right? But there's also applications where you can leverage quantum phenomena to reduce the total amount of memory required to run algorithms. And these two things are really important because digital computers and quantum computers are both universal computing machines or universal Turing machines. So that means that any function can be executed on one, can be executed on the other, or simulated on the other. So a classical computer can theoretically do whatever a quantum computer does, and vice versa. And I say theoretically because like the big caveat there is that it's assuming an infinite amount of memory and an infinite amount of time, which which just isn't really feasible. So they can do everything the same, but the way they do it is different, and the benefits of doing it is different. All right. So how does quantum computers help with memory? Well, the great thing about quantum computers is that they themselves are quantum systems. Technically everything is a quantum system. You and I, classical computers, we're all quantum systems. But quantum computers actually leverage this quantum phenomena in a way that classical computers simply don't. And an interesting thing about quantum mechanics is that each time a new object or a new, let's say like a new electron is introduced to the system, or in our case, a new qubit is added to our circuit, the vector space that describes the whole system, it doubles in size. So really what that means for us is that to simulate a quantum system with the classical computers, the amount of memory scales exponentially with the number of qubits. Why? Well, take this example. So you have two qubits, right? They can be either 0, 1. So the possible states or combinations are 0, 0, 0, 1, 1, 0, 1, 1. Right? That's just like a classical computer or a classical bit. A classical bit can take one value of those four. But the thing about quantum computers is that they could have a superposition of all those values. So you have to be able to represent all those values at once. And that's where this exponential amount of memory comes from. So this table over here, I think really illustrates how crazy much memory, how crazy the memory scales when you look at even just like modern size or modest size quantum systems. So yeah, let's see here. We've got, if you have 23 qubits, you need like 8 million classical bits. I might have done that wrong. And that's like a megabyte. But if you get up to just 53 qubits, which if we're talking about like molecules is like a pretty, like I think a caffeine qubit is like, or caffeine molecule is something like on the order of 33 molecules to simulate, or qubits to simulate. When you're dealing with a 53 qubit system, you're looking at a petabyte of RAM, which is just bonkers. And another thing about this table here that I don't love is that it kind of assumes that you can actually represent each of the amplitudes with just one bit, right? When in reality, these amplitudes are complex numbers. So you're going to need like at least 2 bytes to really represent them. And so you can multiply all these numbers by like 16 to really get a better idea of it. But that's how it scales, and that's where a big advantage comes from. And so that's why the application of quantum computing to simulate quantum effects, or to simulate molecules and like the protein folding problem, or to apply it to pharmacology and drug development. That's why quantum computing has seen a lot of application and interest in that field. But really the point that I'm trying to drive home today is that the theory of quantum computing poses real challenges to our notions of classical computation, or just computation as we know it. It's a fundamentally different type or different method of computation. And what makes this theory really important and worth studying is that it's experimentally realizable. We have built quantum computers, and so these challenges pose a real threat and a real advantage that we can take advantage of. So, well, you know what? I just hyped up quantum computing for a while. So now I'm going to try to take it down a peg. Because as I said, it's important to separate or untangle the reality from the hype. And, it's true for every new technology, for blockchain and AI, they're no different. But a common misconception with quantum computing is that it can do everything a quantum computer can do, but faster. And that's not true. It can do everything a classical computer can do, but it's not faster. It's only faster at a very specific set of things. And another misconception that I want to spend a little bit more time on is that quantum computers can use their superposition to simultaneously evaluate a function on every possible input and just pick out the solution immediately. So there's definitely some truth to this. And what I'm referring to is called quantum parallelism. And it's at the heart of a lot of quantum algorithms. But there's a lot of caveats to it, and it's not as easy as it sounds. So what does that mean? Really, you can evaluate a function on a superposition, or like provided that you can implement your function in a quantum circuit way. And that's called querying an oracle in quantum computing terms. But your output is a quantum state, just like your input was. And, frankly, quantum states are a pain to deal with. That's where a lot of creativity and cleverness comes from when designing quantum algorithms, is how do we take this quantum state and manipulate it so that we can actually pull some useful information out of it. And there's a couple ways to do it. I don't know if I have time to talk about them, but you can't just measure your quantum state and get the result you want, right? Because we talked about the measurement postulate, where measuring collapses the state and destroys all the information. So a couple ways to deal with it would be to measure it a ton of times to try to estimate what your quantum state is, estimate those alpha and beta amplitudes, those coefficients. Or you could just use the output of your quantum algorithm, of your function, as an input to the rest of your algorithm, and then sort of manipulate it later on and maybe try to interfere, maybe try to amplify certain amplitudes of the correct solution. But that's a lot to deal with, and that's a really cool field that we touch on a little bit in the lab. Actually, the hackathon tomorrow. There'll be a cool problem walking through how to use quantum parallelism and use it to sort of drive information about a global property of the function. But we'll get into that tomorrow, so don't worry about it. So that's quantum computing in a nutshell. There's a lot more to discuss, and we'll get into it in nitty-gritty details, don't worry. But now let's shift our focus over to blockchain. So what's blockchain? Well, blockchain's also pretty cool, if you ask me. And it's a pretty new technology, right? So like Bitcoin's been around since, I want to say 2008, and that was really like the birth of blockchain. And it wasn't until a little bit later, when Ethereum developed, that they were able to actually separate out the blockchain from the cryptocurrency. And that is really what we're focusing on here, because it allows you to do a lot of really cool things beyond, send money around anonymously, which is also pretty cool. But the result of having basically pretty new technology is that there's not one great definition of it that I could really find. No one's really settled on what a blockchain is, but they have 5 common properties. And the first one is they're peer-to-peer, right? Their participants can operate without some third party validating their transactions. They're consensus driven, so everybody participating in the blockchain gets to agree on what the collective truth is. It's like a democracy kind of. And cryptography arises a lot in a blockchain, a couple different ways. The way it makes it both secure and transparent and private is by having all participants have a digital signature, which is recorded with all the transactions. And it uniquely identifies them, but it does so cryptographically and privately. And the blockchain's immutable. And that's a big one, is that you can't edit or delete things on the blockchain without there being a record of it. And finally, they're transparent. So data is generally open and participants have access to all the transactions that they were a part of. This figure I really like. I think it sums up really all the big parts of blockchain. And let me just double check what my schedule is here. Sorry. 12:05. All right, I'll do this quick. So we break it up really into a couple of components. One, there's a node, right? A node is just a computer. It's just someone on the blockchain that participates with it, and all these nodes are connected. That's the peer-to-peer aspect, and they build up a network. And each of these nodes has this sheet. It's called a ledger, and you can think of it really as an Excel sheet. It just has a bunch of data on it, and the data is essentially a list of transactions. But each node has their own copy, and all the copies are the same. That's what makes it distributed. And what's critical to most blockchains is that there's no one authority that defines the true value of the ledger. All these participants, all these nodes vote on what the true value of the ledger is. That's decentralization. That's democracy. That's the cool thing about blockchain. And since the ledger can get very big, we sort of break it up into little blocks that we can add one at a time with new data. It makes it a lot easier to verify the truth. So instead of having one Excel sheet, they have an Excel file with a bunch of sheets on it that are all linked together. And how are they linked? Well, essentially just by pointing to the previous one, much like a linked list. If you've taken a data structures course, this forms a chain of blocks, which is why they call it blockchain. And the other thing that's important is that they're immutable. And how that's achieved is basically by introducing two new pieces of information, two new pieces of data to the block. And that would be the block's hash and the block's previous hash, or the previous block's hash, I should say. And what that is, a hash function just maps any input into a fixed sized output. So it maps a sentence or a document into, say, like 256-bit string. And any sort of change to the input dramatically changes the output. That's just a cool property of them. And how that achieves immutability? Well, essentially, each block has its data. It also has a timestamp, not too important, and then it has the value of the previous block's hash. And then all that together is hashed into that current block's hash and appended to the bottom of it. And what that means is that if you were to go back and try to insert a modification, like if I wanted to say that Bhavan and Mustafa sent me a whole ton of money 5 blocks ago, that would change that previous block's hash, right? It would change the data in it, which would change the hash. And that would then change the next block's previous hash, right? Which changes that block's hash. And it just goes all the way up the chain. It breaks everything. And that's how it's obvious that there's been a change made and that there's been some sort of attack, I guess, to the blockchain that's not supposed to be there. And that's how they achieve immutability. And I'm going to touch quickly on, sorry, Spencer, I'm going to touch quickly on what smart contracts and oracles are, because those are the bases of what we'll be dealing with in our blockchain projects. So a smart contract it's a digital version of a legal contract. You know, it has terms and conditions just like a legal contract, but it's written in machine readable code. And then the blockchain automatically executes the contract based on these conditions. So it's got all the benefits of a blockchain. You know, people are honest and they participate fairly because it's out of their hands. It's on the blockchain. The thing is that blockchains are pretty isolated systems, and smart contracts, or just contracts, rely on more pertinent real world data. So like if you're talking about a supply chain system, you might have a contract based on, okay, these goods are received on time and in the proper amount. But how do you take that data and verify it on the blockchain? That's what an oracle is for. And they bring outside world onto the blockchain. But it's tricky because they're not a fundamental part of the blockchain. And what that means is that they don't participate in consensus. They don't have the benefit of all of what a blockchain has. And if you have a faulty oracle, if you're only relying on one oracle, and that happens to get corrupted. So if your oracle is some API, for example, and that API is corrupted, or it's owned by a service that is down for whatever reason, that really centralizes the blockchain, or it centralizes your smart contract and moves away from this decentralized benefit of blockchains. And so that's a big struggle of current blockchain technology. And that brings us really to the end. Thank you so much for listening. That's my presentation, and that's my dog. and I'll pass it over to Spencer for quantum cryptography.